work at the University of Melbourne, but I am very much trained at the Delft University of Technology. I went there for my master's, and you can see we actually graduated, and there's a few people on this call in this picture, which is, yeah, I quite like that. So most of the times when I do any sort of probabilistic modeling for risk analysis and decision theory, I use Bayesian networks, and a particular type of Bayesian network that some of you are familiar with, the non-parametric Bayesian networks. And very often we don't have enough data, so we use structured expert judgment. But since I've left Delft, I became a big fan of what's called the IDEA protocol, and I'm using it in my applications with a flavor of the classical model. And you'll see. So the IDEA protocol stands for investigate, discuss, estimate, and aggregate. And by the time I arrived in Melbourne, it was very much a protocol in itself, but it didn't have a name. So Roger was calling it the Australian Delphi, and we couldn't have that. So we had to give it a name. It is a kind of Delphi in the sense that it has a couple of rounds of estimations, but it starts very much like the classical model with a diverse group of experts that do their own investigation and get a background document or an evidence dossier, as EFSA is calling it now, with all the information and the context of the problem. And then they answer the questions independently. They give a first round of estimates, which very often mean a best estimate and an upper and a lower bound of two quantiles. But what's different from the classical model is that they actually get together, they see an anonymized version of everybody else's estimates, and that's when the feedback and discussion stage starts. And they talk mostly about the reasons behind their numbers. And so the facilitated discussion, extensive discussion is an element of a behavioral aggregation method, but we only took this bit from the behavioral aggregation, and we actually don't want them to agree. We don't strive for consensus. We just want everyone to hear each other's arguments, and then if they hear anything that can change their mind, they can revise their estimates. So they go away after the discussion, and they do another round, an anonymous and individual estimate. And at the end, we do mathematical aggregation. When I'm using calibration questions, I do the performance weighting aggregation, but very often the equal weights aggregation method is used. So in theory, as I said, we ask about the same sort of things as the classical model, a best estimate, which is usually the median, and it's identified as such, and to an upper and a lower bound, it could be the 5th and the 95th, the 10th and the 90th, or if we go Sheffield method, the quartiles, 25th and 75th, depending on who's the analyst and who has different preferences. But we also sometimes do something that Roger likes very much, which is called a 4-step elicitation, where you don't fix the credible interval, but you allow them to specify a confidence. So you'd still ask for a best estimate, an upper and a lower bound, but then you ask about the confidence that they have in that the interval they created will capture the realization, which gives them basically 2 degrees of freedom. They can, if they're very uncertain, they can, take their, increase the interval between the upper and the lower bound, but they can also play with this confidence, which in my experience, it's usually confusing people. So I stopped using this. The reason it was introduced with like that, it was because in a couple of experiments, it showed that when you give them this choice, they tend to be less overconfident. But then all the mathematical acrobatics that you have to do in assuming a certain central credible interval or assuming a distribution to go back and calculate the distribution from those quantiles, we don't really know if that doesn't override whatever benefit this type of question adds. So as I said, in my experience, it's better to stick with the fixed quantiles, which is no surprise, I suppose. We also ask about probabilities as such. So we do ask about, and you'll see an example where we asked about the probability, for example, of a lumpy skin disease outbreak in Australia in the next 5 years. And again, very controversial. We also ask about bounds about that. We don't use them in a probabilistic context, what we do with them is try to flesh out all the counterfactuals that people can think of in terms of what's the worst that can happen, what's the best that can happen. Because I use Bayesian networks and non-parametric Bayesian networks, I sometimes ask for correlations. I don't ask for conditional correlations, just correlations as they are between different variables. And I first ask about a direction of relationship, positive or negative, and then the strength. And we usually don't have calibration questions for correlations. So most of the time I end up just averaging the correlations and then adjusting to get a positive definite correlation matrix. And as I said, I'm a big fan of calibration questions, and that's what I use whenever I can. And what I'm going to be showing you now is just going to be four applications, four of the most recent applications, if you wish, two of which, the ones on top, are applications where we asked about continuous distribution. So all the questions were in terms of a best estimate, so a median and the fifth and the 95th quantile. What's that? Left-hand side, the one with lots of logos. So that's a collaboration between SEBRA and a number of universities in Australia, plus the University of Bergen from Norway. And we were worried about the adaptive capacity of plants and their functional importance to inform management scenarios for different sort of plants in Australia. The one on the right-hand side is a project that was undertaken with the New Zealand's Cawthron Institute, which is about parasites that affect their oysters, their native oysters, and they were obviously very worried about that. Then on the bottom, the DARPA project is a huge project that is we're just finishing now, and it's the University of Melbourne had a team that was called Replicats, and it's a huge project on the replicability of science, where we asked about the probability of certain results in studies, the probability of a direct replication getting the same result as the original study. And then on the bottom at the right-hand side, there's a couple of more recent elicitations that the Australian government, the Department of Agriculture, Fisheries and Forestry wanted us to do very quickly, because there was a bit of a panic for a couple of diseases that arrived in Indonesia, and they were worried that they will cross the border and come to Australia as well. So the adaptive capacity sort of project was initiated by these two people here, Adrian Nicotra from the ANU and John Morgan from La Trobe University, and they were interested in a very simple classification of Australian plants in alpine. So they're both plant ecologists. They were interested in the alpine plants in Australia, and they wanted to know which ones should we basically throw money at. Which ones should have more management than others, and in the idea that the ones that will adapt to a changing climate and are not very important in terms of functional importance in their ecosystems maybe don't need so much help, whereas the ones that are not that adaptive but are very important should receive much more attention. And what we ended up doing was a series of workshops where we basically decided with the experts from these workshops that both functional importance and adaptive capacity can be described as a function of the mean percentage cover of a species now and in the future. So the adaptive capacity will be just what's this adjustment between the future and the current one. So we basically ended up asking the same couple of questions. What's the mean percentage cover of a species given a particular climate scenario? What is it now? And what's going to be in 2050? And for some of those we had data. So we have calibration questions for the alpine elicitation, and we then ended up doing actually 3 workshops, one for the alpine, another for the arid plants, and another for a temperate plants. We had a few experts for all of those, and we asked them, as you can see, more than 100 questions, and they were very, very nice and answered all of them. And once that was done, we could look at, well, plots of this sort where we can look at the current cover on the x-axis and the future cover on the y-axis. So they would be on the diagonal if nothing happens, and look at the ones that decrease in cover. And because very often many of these plants, so the plants are here grouped by in different categories. So we had woodland and heathland and grassland. This is for the alpine plants. And because very often they were close to the diagonal, and many people didn't necessarily agree with that, what we wanted to look at is the plot on top, which is looking at the proportion of responses in the expert group which predicted decrease, no change, or increase, just to see if that average or that combination of answers. And for this one, for the alpine, for the calibration questions that we had, the equal weight combination was very close to the performance weight combination. And we wanted to see if the no change sort of average is because it was an equal split between a decrease, increase, and no change, or where did it come from? And for some species, it was agreement in the expert group, and from some others, it wasn't. But that definitely helped us to choose some focal species for which the decrease was predicted by the majority. And we went away with those ones and looked at, okay, now we know they will decrease in the future, given that aggregated estimate that you have for the future, and a number of management scenarios under the same climate change scenario we had previously. What will the future percentage be if we actually help this, either with taking care of the feral animals, or in the invasive plant species, or fire control, and so on and so forth. So we had six management scenarios. You're not supposed to read all of this. They're just there to say that they were quite detailed, but not too detailed. So they weren't completely prescriptive. And we also had combinations of scenarios that we chose 10 focal species for each habitat, and we had 110 questions for alpine, 110 for arid, 110 for temperate. Again, very nice experts. They did their job, but it was a hell of a job for the facilitators and the analysts to put everything together. So because we had a bit of money, we actually paid a company called Lightning Rock, which made a nice platform for us. And because we're using the IDEA protocol in ecology, we call that IDEA ecology, which is not tacky at all. And we basically facilitated all these data collections through the platform. So they would see things like this. This is a mock-up of the platform, and they see plots like this where they have different scenarios, either management scenarios or present and future, and they can see the differences per user. They're anonymized, and when you hover over the graphs, you will see their comments, and the plots that you see on the right-hand side are just because we're thinking in terms of percent cover in a certain plot, and they're used to going and inspecting those type of plots when they're doing their data collection. So if they say 50%, we'll just show them that that's what it means. That's it for this one. Yeah. So now, and we just finished all the 3 elicitations, and after everyone revises their estimates, the platform will split up an Excel spreadsheet, which can be then taken in R or whatever to do whatever aggregations we want. It will identify the calibration questions, and then we can go on and do our analysis. Then the other application that I was talking about was the one that the Cawthron Institute from New Zealand came to SEBRA and asked for help. And because I was involved, I immediately saw a Bayesian network in their problem. They wanted to know if this Bonemia austria, which is a parasite of oysters and is very common in European oysters, they found a couple of incidents in the native New Zealand oysters, and the combination pest-host was completely new for them. So they wanted to know if it reaches the local population, what's the probability of an outbreak? And after a few back and forth discussions, we ended up with saying, well, it depends how you define your outbreak. So we're just going to look at the number of parasites released in a given month, and they wanted that per year. So we built this model where the green nodes were informed by data, the gray nodes became a bit too much, so we just discretized them and had a couple of scenarios. The yellow nodes were elicited from experts, and a couple of the arcs were elicited as correlations. And as you can see, the output is a functional node, so it's just an equation that gives the number of parasites per month, and that feeds into the parasite abundance node for the next month, and it becomes a dynamic Bayesian network that will speed up the number of parasites per year. Again, there were hundreds of questions. We had calibration questions, and this is just one example where the discussion was extremely important, and it was when we were talking about correlations. Very often we had things like this after the first estimation, and most of this, like things like this, I mean correlations larger than 0 and less than 0 in the same group of experts. And most of these sort of situations just ended up being, oh, I completely misunderstood the question. What I thought about the direction, the different direction. Sorry, I'll flip my estimates, and they all went on the same side of 0, which was very good to see. So, but we wouldn't have identified that. I mean, we would have identified that if we would go back to the experts individually and ask them, did you really mean that, or did you want to add a minus to your correlation? But yeah, the discussion was useful here. We had a hybrid way of doing the IDEA protocol. So I sent them the first round remotely. They did their homework, and the second round and the discussion were done face-to-face in a workshop. We had 120 questions with 16 calibration questions. 2 of them, I think, were, I didn't end up using them after a robustness analysis. And I had 18 experts. I split them in 2 groups. And on the left-hand side, you have the calibration scores of the experts, and then the equal weights decision maker and the performance weights decision maker calibration scores. The top one is the performance weights, the lower one is the equal weights, but they had very similar performance. And because they all liked this exercise so much, they came back with a follow-up saying, okay, now we know what happens if it arrives in New Zealand in a local farm or in a local wild bed of oysters, but where does it come from? So they went for a follow-up project where we looked at the pathway risk. So where do these parasites come from? Well, it depends. They can come with the vessels. They can be on the biofouling, or they can be in the ballast water in the vessels or the aquarium trays. So we had 4 separate pathways, and we looked at submodels that gave us information about the abundance of these parasites at the source, wherever the vessels came from, how many of them actually got into the ship, then how many of them survived transport, how many of them arrived in New Zealand, and how many of them led to an establishment event. Again, we had hundreds of questions, and they actually wanted to do it for 2 parasites, the Bonemia that we had previously and another Perkensis. We had several different hosts for these 2 parasites, and we produced things of this sort. So we looked at the distribution of parasites. We have the Bonemia in one color and Perkensis in another color, and on top we have the number of parasites at source, and then how they decreased, how many of them were entrained, how many of them survived transport, and how many of them were discharged. And that needs to be now linked with when you have a number of parasites that were discharged, in what port were they discharged, and how far there's a population of oysters, such that you will get an establishment event, and connect that with the previous model that we had. Okay, then the project that I said was one of the largest replication of science project that was financed by DARPA. The University of Melbourne had a team called the Replicats team, and the CATS comes from the Collaborative Assessment for Trustworthy Science. And we had 3,000 papers, from which there were a number of claims that were identified as central claims of those papers. And the question was, can we replicate that result, or what's the probability of the same result to be replicated if a direct replication will be chosen. Then the Center for Open Science actually conducted a series of replications for 100 of these claims. So that was our validation data set. And there were lots and lots of people involved in this project. Again, we used the IDEA protocol. This time, the first individual step was to read the paper that we're talking about, read that scientific claim, look at the statistical test, and spend as much time as you have on that paper, and then answer the question about the replication. And again, we had the platform to do that, well, because there were 3,000 of them, and we had at least 5 participants answering for each claim. So we had at least 5 answers per claim that we then had to aggregate in one way or another. My fight for calibration questions didn't go very far because it was very hard to understand what exactly means a calibration question. What do an expert need to know? Or we didn't even have experts, we had participants. What do they need to know in order to answer the probability of replication question? So we ended up with having a quiz that combined questions about replication studies in general, about statistical and probabilistic knowledge, and about meta science. But we couldn't make the quiz compulsory because we already asked so much of these people. So whoever wanted to take the quiz did, and not many people actually did end up taking the quiz. So we had to aggregate this using, well, the standard ones, taking averages, medians, log transforms, and so on and so forth. And we could also have linear combination with weights, but the weights that we produced were basically based on proxies for good performance. And this is the aggregations that we ended up using. So some of them were just averages and medians. Some of them were weighted linear combinations. We had a couple of Bayesian aggregations where we looked at the properties of the study itself. We formed priors based on that, and then updated the priors based on the experts' estimates. And what you see on the left-hand side is a table with all of our aggregation methods and 3 scores, which pretty much give the same explanation, but that's what DARPA wanted. They actually evaluated us with the area under the curve, but we looked at the Breyer score and the classification accuracy. And for us to qualify for the next stage of the project, we needed methods that will have an area under the curve larger than 0.7. So that's what the red line indicates there. What are the methods that do that? But what we had constantly, every time we looked at these methods, was the first to well, you'll see the differences are not very big, but in absolutely all evaluation that we did, the methods that were the champions were the ones where we actually we formed weights based on the breadth of reasoning. So there was qualitative analysis of the comments and of the discussion. There was a code book with different reason codes that was evaluated. And then based on that, we looked at how many of those codes the participants used. So this is we fondly call reason WOG, reason weighted aggregation. And the second version of that is we penalized people if they used exactly the same reasons over and over again for all their claims. So these are the 2 ones that performed well in most of our combination. So that gave us another reason to say, well, actually that discussion, that qualitative bit of comments and discussing, and that actually adds quite a lot. And these are the last 2 ones that I wanted to tell you about. The most recent ones where the department just called basically the director of SEBRA and went, we really want an expert elicitation because in this case, the lumpy skin disease, there was an outbreak in Indonesia, and they really wanted to know what's the probability of an outbreak in Australia. They did this exercise in March 2021, and they had an average from that exercise, and they wanted to know if it increased or not based on the recent events. And they actually prepared this slide and organized all the reasons that we talked about during this elicitation. It was, again, they answered, it was 1 question, 20 experts, I think. They answered the question, 21 experts. They answered the question prior. They filled in a document with all the reasons for this number to be low, high, to increase or decrease. And then we had a 2 hours discussion with these people, and that's the average that they came up with. And then very soon after that, there was an outbreak of foot and mouth disease in Indonesia. And they went, oh my goodness, it's going to come to Australia again. And we repeated the exercise this time for the foot and mouth disease. We had, and this time the increase wasn't very much. And it was interesting to see that what happened in between the 2 exercises is because of the lumpy skin disease outbreak, the biosecurity rules and all the measures that happened for that were so strengthened that the experts thought it's not gonna, the pathways, the risks were pretty much the same as previously, and the biosecurity was strengthened for all of those. And after 2 hours, they pretty much decided that it will increase a little bit, but not that much. And they summarized the safety factors and the risk factors in this way. And that's all. Thanks.